Hello, how are you doing? Welcome to science class. Before you watch this video, please watch the Doppler effect video first. This is the continuing lecture for Doppler effect. In science, the Doppler effect is related to expanding universe and eventually Big Bang theory. If I freshen up to you, the Doppler effect is the change in frequency of a wave. The change of wavelength in relation to an observer who is moving relative to the wave source. It is named after the Austrian physicist Christian Doppler, who described the phenomenon in 1842 for the first time. Here there is a car with a siren, and one girl is here and nobody moves. The siren has its own original wavelength. Now the ambulance car comes toward you, to the girl. The car comes toward you. During it gets closer, the wavelength of a siren gets shorter. Short wavelength is the blue color side, higher frequency, higher energy, higher pitch. Direction to blue color side, the wavelength gets shorter toward the direction of the blue color. We call this blue shifted wavelength. Now the ambulance with the siren moves away from you. The car moves away from you. When it goes away, the wavelength of the siren gets longer. It becomes a longer wavelength. We know the red one has a long wavelength. The wavelength moves toward to the red color side, which has lower frequency, lower energy, lower pitch. Direction to red color side wavelength gets longer to the direction of the red color. We call this redshifted wavelength. What else can the light from distant stars and galaxies tell us? When an object such as a star or galaxy is moving toward us, the wavelengths of the light it emits are shifted toward the blue end of the spectrum. Frequency is shifted higher. This is called blue shift. If the object is moving away, its light is shifted toward the red end of the spectrum. Frequency is shifted lower. This is called redshift. This phenomenon, the shifting of wavelengths due to the relative motion of objects, is called the Doppler effect. You have experienced the Doppler effect every time you listen to a car drive by. As the car is approaching, the pitch is shifted higher, and as it passes and moves away, the pitch frequency is shifted lower. Usually, the Doppler effect is used to tell us the speed of a fastball, to help police to catch people traveling over the speed limit, to permit meteorologists to identify the tracks storms such as tornadoes. So to sum up, if frequency is shifted lower, redshift, it means the object is moving away. If frequency is shifted higher, blue shift, it means something is moving closer, and the amount of shift indicates the speed that object is traveling. Let's think about this. How is the Doppler effect used in astronomy? You are outside at the night sky with a clear sky. You see this pretty shiny yellow colored star here. These yellow stars radiate the light, and the light travels the space and reaches to your eyes. When the light from the yellow star reaches to your eyes, at that moment you are seeing the yellow star. Okay, now nobody moves. Yellow star doesn't move. It has its own original wavelength. What if this yellow star is actually moving toward you? You know, when you observe the star is located really far away, and it really looks like a small dot. So even though this yellow star moves toward you, you will not see any size change. It still is a small yellow dot. We don't know. So if you are a scientist with a spectrometer, you can observe this yellow star spectrum based on Doppler effects. So star comes toward you, gets closer, wavelength gets shorter. Shorter wavelength means that the wavelength moves to the blue color side with a higher frequency, higher energy, higher pitch. We call this blue shifted. Therefore, wavelength changing to the direction of blue color side, blue shifted. What if this yellow star is moving away from you? We cannot find out its movement even through the telescope. So star moves away from you. This wavelength gets longer. Longer wavelength means wavelength changes to the red color side with lower frequency, lower energy, with lower pitch. Direction to red color side means red shifted of the Doppler effect. So Doppler effect with a star or galaxy, or star and the galaxy. In the astronomy, with spectrum, we have a spectrum with the spectroscopy. The scientists can observe the wavelength changing toward the blue color side. We can see the wavelength changing here in the spectrum. So star comes to you, wavelength gets shorter, direction to the blue color side. We see blue shifted in this spectrum. What about our interpretation about this spectrum? Our interpretation of the Doppler effect here, wavelength gets shorter, blue shifted, star comes toward you. It means the distance between the star and you gets closer. What about this case? If star is moving away from you, the spectrum here shows the wavelength changes into longer side, red color direction. This does not mean red color itself. It means the red color direction, so-called red shifted. Star moves away from you, wavelength gets longer, direction to red color side, red shifted. The interpretation of the Doppler effect, wavelength gets longer, red shifted, which means that object goes away from you. The distance between the object and you gets further apart. So light from approaching objects is blue shifted. The waves crowd together. Light from receding objects is red shifted. The waves are spread further apart. However, in real astronomy, we generally find redshifted Doppler effect a lot. We observe lots of redshifted galaxies, a lot more than blue shifted galaxies. So we see a lot of redshifted stars or galaxies in the night sky. Most of them are moving away from us. One thing we need to think about is who moves. Do you think only star is moving away? What about us? Is our galaxy Milky Way is really moving away too? Let's consider this red circled galaxy is our Milky Way and we are in there. Actually, all the galaxies are moving apart, separating farther and farther away. So all of the light from stars and galaxies that reaches the Earth is redshifted. What does that mean? It means that everything is moving away from us. How can everything be moving away from us? Only explanation for that is the universe is expanding. And if the universe is expanding, then long time ago, it must have been much smaller. The expansion began about 13.7 billion years ago with the Big Bang. Then we can ask a question. Does the size of the universe change? So light from the galaxies displayed a redshift. Compared with the nearby stars, Edwin Hubble recognized the redshift as a Doppler effect. Galaxies are moving away from Earth. No galaxies are moving toward the Earth. The expanding universe theory, the whole universe is expanding. Analogous to bread dough, galaxies farther from Earth are moving away faster than galaxies close to Earth. So if we have a bread dough here with the raisins in there, the bread gets bigger and bigger, spreading apart. So the distance of the raisins are farther apart. Note here that there is no change of the numbers of raisins. So now we know our universe gets bigger and bigger. Then what about the past? What about the starting point? Our universe must be started from the very small point, singular point. Our universe started from the single point with all matters and energies compressed. Then something happened in 13.7 billion years ago. It could be an explosion, nobody knows. Anyhow, something started from the single point and there become a space in our universe and keep expanding so far until now. The Big Bang theory proposed that all matter and energy in the universe started out as a very small single point. It exploded and has been expanding since then. Hydrogen atoms formed within a few seconds. After 3 minutes, light nuclei, helium, lithium, beryllium were created by Big Bang nuclear synthesis. Thank you very much.